Today's lesson, we're going to use statistical process control. So statistical process control uses something called inferential stats. So with inferential stats, you can generalize and evaluate a population based on sample data. The other thing you could do is what is called descriptive stats. So descriptive stats would mean say I took this whole jar of peanuts, and my goal here is to find, what is the range of peanut lengths. What do I mean by lengths? So if I took this ruler and I were to measure this in millimeters, I'm measuring the length of this peanut. I don't know if you can see that, but I'm measuring the length of this peanut, and it's about 16 millimeters. So descriptively, I could measure every single one of these peanuts. Or I could just randomly select 30 and do it the inferential way. And it turns out doing it the inferential way is actually a better way to do it. It's more likely to yield good results. The problem with having people measure every single peanut, well, obviously besides the obvious thing that it's going to take a long time to do that, is that you make errors, and it's very difficult to do this to get 100% accuracy. So we're going to use statistics to predict it instead. When I'm done, I'm going to be able to make predictions about this entire jar of peanuts based on the 30 that I measure. 30 is the smallest statistically valid number that you can really use without getting into trouble. It's important to realize that I'm just essentially sampling this one container. If I were to go to Wegmans and take some random, take one peanut out of 30 containers, then I could make a prediction of the entire lot of peanuts at Wegmans. Or if I were to go to several stores across the Northeast, then maybe I could use those 30 to make predictions about the entire population of the Northeast. Once I start taking data, I'm going to want to use a table similar to this. You'll probably want to use Notability's graph paper feature. But I'm just going to start the peanuts, and I'm going to number 1 through 30. We'll just kind of skip to number 30 here. But I'm going to measure the length. So say I measure the first one and I get 19 millimeters, which is what I got. Then maybe the second one is 21, and then maybe I get a 17, maybe I get a 22, all the way to the last one, and I'll say the last one's also 17. We're going to skip using the bin column, but we're going to go back to that later. Probably next lesson will be on histograms, and we'll be using the bin feature. But next column says x minus x bar. X bar simply means the average. And so you're just going to do all 30. And I don't want you to use a spreadsheet. I want you to do this by hand with your calculators. Do the average. It takes some time, but there's a method to my madness. So let's say I go through this and my average value is, 18. So my average is going to be 18. And so x minus x bar, the first one would be 19 minus 18. That would be plus 1. Then 21 minus 18 is plus 3. 17 minus 18 is negative 1. 22 minus 18 is 4. So I'm just doing this for all these values. This one's negative 1 again. The next column, I'm simply going to square that value, which does make them all positive. So this would be a 1, this would be 9, this would be 1. You'll probably just do this on your calculator. And the last column is what we're really looking for, which is the standard deviation. Our standard deviation formula is the square root of the sum of x minus x bar squared over n minus 1. Well, n is the number of samples, so that's just going to be 29 then. N minus 1 would be 29 in our case. You're going to need the sum of x minus x bar squared. So that would just be the sum of this column. And maybe when you do that, you enter this, you divide it by 29, you take the square root. Maybe when you do that, you get a standard deviation of, I don't know, we'll say 2. And that would be 2 millimeters. So this number is really 2 all the way through because it's one number for everything. What it really means is if my average value is, in this case, 18, it's saying that the average distance any given point is from that 18 will be 2 millimeters. So you have a tighter distribution if in the case you have a standard deviation of 2, whereas if you had a standard deviation, say, of, I use a different color, say you had a standard deviation of 5, something like that, the numbers would be much further away, and you would just have this really big range of possible different data points. To make a control chart, I'm going to use some graph paper and I'm going to make sure that I have, I can number it from say 0 to 30 because I'm going to be plotting my data. And my y-axis is going to be the length, in my case, millimeters. I mean, you could use inches if you wanted to for this project, or centimeters, but I chose to use millimeters, so I'm going to go 0. And then maybe the top or the highest number I recorded was maybe 26, so I'll put that up here. And I'm then going to plot every point in order. So I'm going to do 1, 2, 3, 4, all the way to 30. And I believe my first one was 16, so that would be maybe around here. And then, I had different ones going through. Eventually I get the 26. And I'm just simply plotting my points. Once I plot my points, I'm going to want to also show the average. I think I said my average was 18, so maybe I'll just say average 18 here, or I could have just said x bar. And then I want to show my control limits. So when I talk about control limits, I'm talking about plus or minus 2 sigma, plus or minus 3 sigma, and we could go to plus or minus 4 sigma. In industry, they go all the way down to plus or minus 6 sigma. Now, what am I talking about for that? I'm talking about for plus or minus 2 sigma, it's just, that's 2 times the standard deviation. Now, the standard deviation I said was 2, so my plus or minus 2 sigma would be plus or minus 4 millimeters. Plus or minus 3 sigma would be 3 times s, which was 2. So it would be plus or minus 6 millimeters. And then plus or minus 4 would be 4 times standard deviation, or plus or minus 8 millimeters. Now, plus or minus what? So it's plus or minus the average. So here I would have for my plus or minus 2 sigma limits, I would have a range of 14, that would be 18 minus 4, 222. And I would come up on the chart, and I'm going to highlight this. Well, you can use colors in Notability, so I would suggest you do. So I'm going to go, say, 4 to either side of the average. And then I'm going to want to actually label that as well. So this, and you can do a neater job than I'm doing here, but you could somehow label this as plus or minus 2 sigma. And then I want you to also label plus or minus 3 sigma. So plus or minus gives you another 2 beyond that. So maybe you could just, do red on either side. And then however you want to label that. I'm going to really botch this up, especially since I grabbed the wrong tool. But you're going to label that as plus or minus 3 sigma. Now, what plus or minus 2 sigma means is that means that's going to encompass 95% of your data points. The plus or minus 3 sigma is going to encompass 2,700 parts per million, or 99.7% of your data. So, and then that essentially means, since you're only doing 30, probably all your data points will fit in that range. We're essentially done with today's project, but just to give you an idea of what it means. So if I come up with plus or minus 3 sigma limits on my peanut example, and I get plus or minus 6 millimeters, that tells me that the entire jar of peanuts, 99.79% of the jar, will fall within that range. And I can predict that just using 30 pieces. If I'm a tool operator at a factory and maybe I'm turning a shaft on a lathe to a certain diameter, what the lathe person will do, and maybe they're making thousands of these, so they don't need to measure every part. They'll measure maybe every 10th part. And every 10th part they'll put on their control chart. You can do the control charts by hand, but nowadays usually there's software that assists you. So you'll enter that diameter that you recorded for the 10th piece. And when you do, it just indicates if it's within range. And it can also indicate if you're starting to slip out of the range, and the operator can notice that. And usually that might be because there's tool wear or some problem with the lathe that needs to be fixed. But it gives you an advance indication that your process is out of control.